Hey guys, it's Mr. Tracy. I hope everybody is healthy and their families are healthy. We're going to try something new starting this week. We'll see how it goes. So remember these books. I hope you all have them. If not, I'm going to attach this lesson, which we are going to be doing 10-4 today. Which looks like this. I'll attach that to Microsoft Teams. If you do not have your book, that's okay. You can always print it out or just follow along with the Word document that I'm going to attach to the assignment. All right. So today we're going to talk about polynomial identities. Polynomial identities are expressions consisting of addition and subtraction variables and coefficients, all raised to non-negative integer powers. Okay, so it can only be a polynomial if it's non-negative or otherwise positive, and it's got to be an integer, which means it's got to be it can't be a decimal. Okay, it's got to be a whole negative or positive number. All right, so exercise number 1 should be pretty easy. Which of the following is not a polynomial expression? Explain why your choice fails to be a polynomial. So let's take a look at our answers. See if you can take a second, press pause, and figure out which one of those is not considered a polynomial expression. All right. So we're looking for an expression that has non-negative integer exponents or powers. Okay, so remember it can only be positive exponents. So this one is definitely a polynomial. So is this one because I got positive exponents here. And here it looks like I have negative exponents as well as a fraction exponent. Fraction is not an integer. So this is the one that we are talking about that is definitely not a polynomial expression. So I just watched back that video and I noticed you can't really see the top of what I was doing. I was wearing this cool little headgear piece over here and it was really far away from the ditto, so now I am just going to be holding the camera here. Let's see if this works. All right. So we know what a polynomial is from the first example that we just did. All right, non-negative integer powers. So choice 3 was the answer. Hopefully you could see it now. All right. Now we're going to move on to identities. This is something that we did earlier in the year that you should be familiar with. An identity is an equation that is true. Those are the two key words here. An equation that is true for all values of all variables. All right. So if it's an equation that's true, that just means that I have to have two equal values on both sides. All right, so two equal values on both sides. The left should be equal to the right. I should see two of the exact same things on the left-hand side of the equal sign and the right-hand side. So exercise number 2 says one identity that you should be familiar with is x squared minus y squared equals x minus y times x plus y. Okay, prove this identity by manipulating the right side of the equation. All right, so the reason that we might be familiar with this is basically just dots, the difference of two squares. Okay, if you have a perfect square minus another perfect square, remember we're able to factor that by doing x plus y times x minus y. Now we're just going to show that that's true. It says prove this identity. And we're going to do that by manipulating the right side of the equation. All right, so we're going to leave the left-hand side alone. X squared minus y squared equals, what do you think it means by manipulate this side of the equation? Well, I have two sets of parentheses next to each other, so what if we multiply these? And the only way that we know how to multiply a binomial times a binomial would be FOIL, or double distribution. All right, so 4 different multiplications here. So x times x is x squared. X times y, that's plus xy, minus y times x, which is just minus x times y. And last but not least, I have negative y times positive y. That's negative y squared. All right. So I have x squared minus y squared equals this mess on the right-hand side. What do you notice we can do with two of those terms, the two middle terms? What's going to happen to them? Well, since I have a positive xy and a negative xy, they are going to wipe each other out. And guess what? On the left, I have x squared minus y squared. And on the right, I have good old x squared minus y squared. Are these two things exactly the same? Yes, they are. So, this is a true equation. Therefore, it is an identity. All right, let's see how that looks. Is this recording? Yes, it is. Sorry about that. All right. So, exercise number 3 is a little bit trickier. All right. We're going to do kind of the same thing. We're going to algebraically prove that the left-hand side of the equation, x to the third plus 9 over x to the third plus 8 equals 1 plus 1 over x to the third plus 8. Okay. So, we have to try to get this side of the equation to look like this side of the equation. All right. Well, it looks like I have a fraction over here, and I have a fraction over here. Oh, I'm sorry. I have a fraction over here, and I have a whole number over here. All right. But remember, the only way that I could add two things together, and one of them is a fraction, is if I have common denominators. So I got to get this 1 to have a denominator of x to the third plus 8. My dogs are barking at each other and wrestling. I have to get this 1 over here to get a denominator of x to the third plus 8 in order to add these two things together. Think about what a common denominator could be. Well, how about x to the third plus 8? All right. Remember how I get a common denominator? I'm looking for my pretty pink pen. Okay, how do I get a common denominator? Well, I can manipulate this 1 by multiplying the top by x to the third plus 8. But remember, whatever I do to the top, I have to do to the bottom as well. X to the third plus 8 down here also. All right. So, what am I left with? All right. The left-hand side, we're going to keep exactly the same. I have x to the third plus 9 over x to the third plus 8. That's just the left-hand side of the equation. And now this 1 is just going to turn into x to the third plus 8 over x to the third plus 8 plus, don't forget about this fraction over here, 1 over x to the third plus 8. All right, the reason that I do that, okay, is because now I have common denominators of x to the third plus 8. Now I can add the tops. Remember when we add fractions, okay, we add the numerators, the denominators stay the same. So I'm basically combining like terms. My only two like terms in the top are this 8 here and this 1 here. And when I add 8 plus 1, guess what I'm going to get? X to the third plus 9. So what's my final answer going to look like? Well, I have x to the third plus 9 over x to the third plus 8. Whoops. On the left, I just brought that over from over here, equals x to the third plus 9 over x to the third plus 8. This side is exactly equal to this side. Boom. We just proved it. All right, let's move on to exercise number 4. We got a couple of different parts here. All right. Same kind of thing. It says prove the following identities. All right, so for part A, we have n times n minus 2 times n plus 2 equals n to the third minus 4n. All right, so what we want to do is we want to manipulate one of the sides of the equation, probably this side. Okay, there's nothing I could really do over here. All right, and I see this is all multiplication here, n times n minus 2 times n plus 2. So let's multiply it out and see if it's equal to n to the third minus 4n. All right, I'm going to do my double distribution first. So I have that n on the outside, and I'm going to double distribute n times 2, negative 2 times n, negative 2 times positive 2. And what am I left with when I multiply that out? Well, I have n squared plus 2n minus 2n minus 4. And then the right-hand side of the equation is n to the third minus 4n. All right. I'm going to go ahead and combine my like terms here. I get n times, n squared. 2n minus 2n, easy enough. They're going to cancel each other out. And then I have n squared minus 4 equals n to the third minus 4n. Anything I could do to the left-hand side of the equation? I certainly think so. We have this n on the outside here. Let's multiply that in to the parentheses, and guess what I'm going to get? N to the third minus 4n. And is that equal to the right-hand side? You bet. So, this is definitely an identity. All right, part B now. I know you guys love fractions, so you guys should have fun with this one. We have 1 over 4x plus 1 over 2x squared equals x plus 2 divided by 4x squared. Remember, we're being asked to prove that this is an identity, meaning that this side is equal to this side. So take a second and think, which side of this equation could I manipulate a little bit to get it to look like the other side? I am probably going to work on the left, okay? I can definitely add those two fractions together. I can't do it yet, okay? Because what do I need in order to add two fractions together? I need a common denominator, okay? So we got to think, I have a 4x over here, I have a 2x squared over here. What can I get them both to be by multiplying? Well, my common denominator is probably going to be 4x squared. If I can get this to be 4x squared and this to be 4x squared, I can add these two fractions together. So take a second and think. Shut up! Take a second and think. What can I multiply this fraction by to get the denominator to be 4x squared? Dogs. Hey! Quiet. Enough. Well, I can multiply this fraction by x over x. That'll be 4x squared down here. And what does this one need to have a common denominator of 4x squared? I think we're just going to multiply it by 2 over 2. All right. Well, multiply it out. Let's see what we get. X times 1 is x over 4x squared. Plus 1 times 2 is 2 over 4x squared. That is good. Equals x plus 2 over 4x squared. All right, now I can add these two fractions together. Remember, when I add fractions together, denominators stay the same. Add the top. So I have x plus 2 over 4x squared equals, look what's over here, x plus 2 over 4x squared. Boom, just proved another one. All All right, let's move on to the next page. Dogs. All right, what do we have here? Which of the following polynomial equations are valid identities? All right, so we have A, which is 5b minus 2 squared plus 4. Let's see if that's equal to 25b squared minus 20b. We'll do that one first.
Eleanor.
All right, so like I said, this side there's really nothing I can do. I can't combine like terms or anything. There's no multiplication to be done. But over here, I can certainly multiply this out, 5b minus 2 squared, okay? And then whatever that turns out to be, we'll add it to 4, and let's see if it's equal to this. All right, I'm going to work on that over here. So remember, 5b minus 2 squared is 5b minus 2 times 5b minus 2. And we're adding that to 4. And we're seeing if that's equal to 25b squared minus 20b. All right. So let's double distribute, see if you can do that on your own. You should not just be copying notes, you should be working along with me. So take a second and FOIL that out. Alright, minus 10b minus another 10b when I multiply these guys together. And last but not least, negative 2 times negative 2 is positive 4. And then don't forget about this positive 4 up here. Equals 25b squared minus 20b. Alright, now the only thing left to do over here is to combine my like terms. I have 25b squared. Negative 10b minus 10b, I think that's negative 20b. And a positive 4 plus 4, I think, is plus 8. So, on the left-hand side, I have 25b squared minus 20b plus 8. I cannot combine these two because the 8 does not have a b on it. And then I have 25b squared minus 20b. All right, so they're close, okay, but they are not exactly the same. So, is A a valid identity? No way, Jose. So now we just got to check to see if part B is a valid identity. Take a second and do that while I try to get my purple pen. I don't know what I did with it though. Found it. All right, so now we are working on part B. All right, I have, looks like the only thing this side is there's nothing I can really do to it. Okay, so I'm gonna multiply this side out to see if it's equal to this side over here. All right, so we're gonna double distribute. Whoops. All right, we'll do our 4 multiplications. All right, and when I multiply that out, I get 2x squared times 2x squared, which is 4x to the 4th. 2x squared times negative y squared, I think, is negative 2x squared y squared. And then y squared times 2x squared is plus 2x squared y squared. And negative y squared times positive y squared is negative y to the 4th. And we want to see if that's equal to this side of the equation, which is 4x squared minus y squared. Alright, well, what's going to happen here? I have negative 2x squared y squared plus 2x squared y squared. They are definitely going to wipe each other out. So I'm just left with 4x to the 4th minus y to the 4th equals 4x squared minus y squared. Again, super close. Well, not as close as we thought, but these two sides of the equation are definitely not exactly the same. So, is this an identity? Absolutely not. So, part A is not an identity. Part B is not an identity. Which answer am I going to circle? I think it's choice 4. Neither A nor B. All right, let's move on to exercise numero 6. Is the following proof valid? Now, the Regents loves these types of questions. Oh, yeah, I forgot you don't have to take the Regents this year. Lucky. Well, you still are required to do the work here if you want to pass. So, you got to be able to do something like this. Is the following proof valid? If not, what is the invalid step in the proof, and explain what they did wrong? All right. So what we're kind of doing is following this student's work to see if they made any mistakes. Okay, going step by step. We're basically grading it like a teacher. All right. Take a second and look over all those steps. See if you see anything wrong. All right. Well, it looks like they expanded this x minus 2 times itself. That's a good sign. Remember, x minus 2 squared is really x minus 2 times x minus 2. That is a good start. I think that is correct. Get my eyelash out of there. Next, it looks like they double distributed. And they got x squared minus 2x minus 2x, and then negative 2 times negative 2 is positive 4. That looks good to me too. What'd they do in their next step? Kind of looks like they combined like terms, and they got negative 4x. Do you agree with that? I certainly do. So far, so good. Then it looks like they multiplied this binomial here times this trinomial. Now, the way that we were doing that in class was, I don't know if you remember, it's been a little while. Remember, we would set it up like this in this little fancy box action, and we would put our trinomial across the top, x squared, negative 4x, and 4, and 4x, and negative 3. Okay, and then we would multiply it out, all right, and we would end up combining our like terms. So it looks like they got, well, what would we get? Let's see, 4x to the third, x squared times negative 3 would be negative 3x squared, all right, negative 4x times positive 4x I think is negative 16x squared. Negative 3 times negative 4x I think is 12x. 4 times 4x, 16x. And 4 times negative 3, I believe, is negative 12. All right? So they got 4x to the third. That matches up. See if you could find where I went wrong. What happened here? 4x times negative 3, x squared minus 4x plus 4, or negative 16x squared. That should be 12x, I agree with that. I think I did this right. Let's see. All right, let's match up to see. We got 6 terms up here. Let's see if these 6 terms match up with these 6 terms. They got a 4x to the third. We got that here. Check. All right. We got a negative 3x squared. So did they. Check, check. They got a negative 16x squared, and so did we. All right. They got a positive 16x. Well, so did we. So far, so good. They got a negative 12. We got a negative 12, but uh-oh. I see an issue. When we multiply negative 4x times negative 3, we got positive 12x. This student got negative 12x. So, is the following proof valid? Well, I don't really think so, but we have to explain why. All right, so the way that we would explain this on a Regents would be, is the following proof valid? We got to answer the question. No. Not a valid proof because when negative 4x is multiplied by negative 3, you should get 12x, not negative 12x. All right. Okie dokie. All right. I'm going to skip over number 7. I'm not really in love with that question, but I do like number 8 because those of you that took geometry last year, which is pretty much all of you have taken geometry at some point. Most of you took it last year. This integrates a little geometry action into Algebra 2. So it says sometimes identities can have geometric connections as well as algebraic. The Pythagorean theorem gives us ample identities. And those of you that were lucky enough to have me last year definitely remember Pythagorean theorem, right? Think about it. What's Pythagorean theorem? I think it's a squared plus b squared equals c squared. Do you remember what you used that for? Remember these guys? Right triangles, where you have 3 sides, obviously, of the right triangle. Remember what this guy was called across from the right angle? This was your hypotenuse. All right. And then we had 2 legs. All right. The C is always the hypotenuse, and the 2 legs are always the A and B, and those ones are interchangeable. But the hypotenuse always has to be C. All right, and I'm pretty sure all of you kind of remember that. Hopefully, actually, you'll probably remember that for the rest of your life. A squared plus b squared equals c squared. All right, so exercise number 8 says Jerome uses the polynomial identity. Whoa, look at this mess. X squared minus y squared plus 2xy squared equals x squared plus y squared to generate the Pythagorean triple 9, 40, 41. What values of x of y did he use to generate the values for the 3 sides of the right triangle? So, let's think about this. It says to generate a Pythagorean triple of 9, 40, 41. What the heck is that? Well, remember there were those special right triangles that your teacher or me used to talk about. This one popped up quite a bit. The 3, 4, 5 job. This one popped up a bunch. The 5, 12, 13 action. Okay, the Regents loves these 2 triangles. I drilled that into your heads. Okay. Well, one of those other special triangles that pops up is the 9, 40, 41. Okay. Because if you plug this into the Pythagorean theorem, okay, and let's just do a little test run. 9 squared plus 40 squared equals 41 squared. All right, let's check that out. Well, 9 squared, I remember. 9 squared is 81. 40 squared is 1600. And 41 squared is 1681. And guess what? When you add this side, you figure out that, oh, this makes sense. Okay? So 9, 40, and 41 can be the three sides of a right triangle. All right? Now, what is this mess that they gave us here? This looks pretty ugly, but it's not. Here's why it's not. I just stabbed myself with a pen. Oh my gosh.
You bleeding?
No, not bleeding. Here's why it's not too ugly. All right? We basically have the Pythagorean theorem here. We have a number squared plus a number squared equals a number squared. So this is your A, this is your B, and this is your C. Okay? X squared minus y squared is A, 2xy is B, and x squared plus y squared is C. This is the Pythagorean theorem. A